Okay, today I want to cover a topic that it's kind of hard to describe if you don't understand how meters work, but I'm going to do my best here. So this was kind of spurred on by a problem the customer or the owner of this bottom radio thought he was having. That problem being wasn't receiving correctly. Well, actually, it receives really good. It's a realistic Navajo TRC 457, has a Uniden UPD 858 chassis in it, and it's a good working radio. But he said he didn't think the receiver sensitivity was very good on it. So compared to the radio that's on top of it, which is a current production, that's a new radio, which is a President Lincoln 2 Plus. You know something? They both sound the same. Doesn't matter what signal level you put into it. And I've got it currently hooked up to a communications test set, so a signal generator. Now, the problem is the meters. I think that's what was throwing this guy off. The meter in this radio is horribly inaccurate anywhere except for the point in which it was calibrated. And that's the key to remember here. Calibration. That calibration point. Analog meters are only 100% accurate at the point you calibrate them at. Anywhere else on the scale is going to be some level of inaccurate. It's going to inherently have some level of inaccuracy. Precision analog meters. Now these are cheap. Honestly, both of these things are cheap. Both of these products are consumer level products. They're not commercial products. It's not an instrument, an instrument meter like that AC voltmeter there, or a Synad meter, or signal generators, or stereo PA stereo amplifier analyzers, or commercial watt meters. These meters cost tiny fractions of what those really expensive meters cost. Now, even those really high-end meters, they're inaccurate as well. Anywhere except from the point where they were calibrated. And only at that exact point are they accurate. Now, those meters, pretty much anything in instrumentation, you would probably never notice, and it honestly wouldn't be recognizable by anybody, the inaccuracy at any point on the scale, because they are precision meters. So their error of inaccuracy is going to be fractions, tiny fractions of a percent for really good meters. Could be 0.5%, even be 0.1, or even lower, if you get really, really high-end meters. Meters like this, on the other hand, can be horribly inaccurate because they only cost the manufacturer probably pennies, where the meters used in a lot of instruments, just the meter movement itself could cost $50 or $100 or more. Meter like this may cost the manufacturer 25 cents, back when they were building it, and that was it. So, huge difference in price scale. So, you would expect these to be more inaccurate. The other problem is they can have problems. They're mechanical. They're, again, not precision meters, so they can wear out. Anybody that's owned old CBs is probably familiar with the needles getting stuck. Common problem. I've done a whole separate video. It's actually a very popular video on how to unstick analog meters when they get stuck. It's very simple. Anybody can do it. You can fix your own radio, and lots of people have taken that video, watched it, and they've repaired their meters. So hey, good for you. It's, there's something that anybody can do. But I want to demonstrate the inaccuracy of one over the other. The difference here is this is an old analog meter. This is a modern radio, so it doesn't have an analog meter. It has a digital display, so it only represents the S signal, or the incoming signal strength, with bars. Okay, so there's a bar for S1, there's a bar for S2, there's a bar for S3, but there's nothing in between. This meter kind of is what you would almost consider like an infinite reading meter. There is no, spot where it just goes from S1 to S2. It's kind of fluid flow like, okay, so there's any point in between. But the problem with meters like this is they're mechanical, and the way they operate is they have what's known as a clock spring inside, or at least that's what I call them, a clock spring, because it reminds you of the coil or wind-up style springs you find in clocks. They use those on meter movements because if you were to take that little spring that's usually only about that big around in there, little wound-up spring, and unwind it, it's really long. Relative to the size of the meter, it's fairly long. Well, when you coil that up, the meter needle only moves from this point to this point. It doesn't move very much. So you've now taken a really long spring and spread that tiny amount of movement of that spring over that entire length of the spring. So that's how they can come up with a fairly accurate amount of tension on the needle, because the needle is operated by electromotive force. So electricity is applied to the back of the meter, creates an electromagnetic field, and that's what actually moves the needle up. And what keeps it from just going full scale is the tension of that spring. But you want that tension to be exactly the same over the full scale. Again, cheap meters are going to be so-so. High precision meters have really, really accurate springs in them. Also, you have the pivot points, where in precision meters they'll usually be jeweled. Ones like this, yeah, it's just it's two needles basically going into a metal block, and there's friction there, so there's lots of things that can go wrong with cheaper type meters. The meter in this one, like I say, has no point in between. It just goes from S1. When it finally gets the signal that's S2, it lights up that bar, and then the S3 bar, and then the S4 bar. The big difference is how inaccurate this one is once you start to get downscale, and that's what I think threw this customer for a loop, basically. This signal meter, I think it takes like an S5 signal coming into this radio to read S1. That's how far off it is. From the bottom of the scale to the S9 point, I calculated that it was, I think, 24 point something dB inaccuracy, I think, from the S9 point to the bottom of the scale. It's perfectly accurate at S9 because that's where I calibrated it at, and it's where you're supposed to calibrate the meter. The problem is the farther you get down scale, the more inaccurate it gets, and it gets horrible by the time you get to the bottom. And at 24 point something dB inaccuracy, that works out to, like, God, probably, trying to do this math in my head, what would that be, 200 and, oh man, 220, 230 times, I think, if I'm doing the math in my head properly. Yeah, it'd be about, because that's a huge, that is an enormous, the huge isn't even the right word. I'll use my aunt has a term she made up, hubigous. It's a hubigous amount of error. It's like I say, it's going to be around 220 to 230 times error from S9 to the bottom of the scale. So S9's perfectly accurate. By the time you get to the bottom of the scale, it's 220 to 230 times inaccuracy. So, but I want to demonstrate how that. So actually I got the signal going in a little bit. Oh, I don't have it at the right point, that's why. Put the communications test set. So actually let me show you. So what I have going here, this is a splitter combiner, okay? So this has 3 ports. There's an in port, or the signal port, and then it has 2 output ports. So this is a splitter, okay? So any signal that comes in this center point is evenly divided between these 2 ports, and they're commonly known as a 3 dB splitter because there's 3 dBs worth of loss when you split that signal out to two different cables. But what that ensures is the signal that's coming in here from the communications test set is the same going into both of these devices now. So I've set the signal level to an S9 signal. So if you remember, S9 is supposed to be minus 73 dBm, okay? We're not going to get into the bullshit controversy of, no, that's not what it is. That's the international standard. If you don't like it, tough luck on you. That's what the internationally agreed to standard for S9 for signals 30 megahertz and below is. minus 73 dBm. With that out of the way, so we're feeding in a minus 70 dBm signal. Okay, you can see minus 70, but remember, this is a 3 dB splitter. Okay, so there's 3 dB difference. So that's why we've made basically a calibration factor with the signal that I'm putting in to these radios of 3 dB. Instead of minus 73, it's minus 70 because of that 3 dB difference. So that signal is being split going to both these radios. And as you can see, we have the needle right there on S9. I don't know if you can see the needle. I'll go off channel. There you can see it moving. And it goes right to the center of the S9. And we have this one up here reading S9. Now, watch what happens as I start to turn the signal level down. Okay, we'll try and get that needle right about in the middle of S3. Okay, you can see this one is reading S3. This one's reading S7. If we get to S1, okay, that's now center of the 1, and S1, we're showing an S6 on this radio. Yeah, there's a 5D, and this radio is very accurate over its full scale. Where this one, the farther you get downscale, the more inaccurate it is. And like I say, by the time you get down here to the bottom point, there's 24 points, I think it was like 24.8 or 24.9 dB of error. It's just an enormous amount of signal difference. So that's why I think this customer was thinking this radio wasn't receiving very well, is because the signal coming into it was strong. He could hear the signal. The problem is it's not being reflected on the meter until basically the needle on this radio is not going to move until you get approximately an S5 signal level coming into it. Where this one, on the other hand, it doesn't have a needle, but the display is fairly accurate. And the reason, and I should even make sure I make this clear, not all modern radios are accurate either. This one is very accurate. Okay, the program that they use in the Lincoln 2 Plus, or the Lincoln 2, is very accurate for a linear reading over the full range of that meter. How they can do that in a digital style radio is the analog signal, so the signal you're receiving off the air comes in the antenna jack. A small portion of that is sampled. That goes to an A to D converter, an analog to digital converter, because you have to remember this has a microprocessor in it. Microprocessors don't operate off of analog signals, they operate off of digital signals. So the A to D converter converts that analog voltage that it's sampling at the antenna jack for the incoming signal, converts that into a digital signal that the microprocessor then understands. Then there's a calibration table inside that program, and it knows once it receives, once the A to D converter has converted a certain amount of signal level to this digital data, you need to display an S1 signal, or an S2, or an S3. But what that allows the engineers to do is actually calibrate each one of those bars individually. So they can inject an S1 signal into the radio, take a measurement, and they'll know this is what signal level we need to make that first bar illuminate. Inject the S2 signal level into the radio. This is how much of signal we need to illuminate the S2 bar, and so on. Where analog meters only have one calibration. Now, two-way radios and receivers as well, communications receivers, like I say, 30 megahertz and below, the international standard is minus 73 for S9. Now, when you're doing stuff like laboratory-style meters, they always have you calibrate those meters at full scale. So any test equipment you ever see, when they're calibrated, that's what they're calibrated for. Maximum accuracy at full scale. And that's why they'll also usually tell you the meters, if you look at a lot of precision meters, now I'm not talking about just the meter head, the actual instrument itself. They'll always tell you not to use like maybe the bottom 10 or 15% of the scale, because it's like this meter, it's not accurate at that bottom point. They'll tell you to move your meter range down the next, down to the next scale. But like I say, there's only one, you can only calibrate this meter. It's arbitrary. It doesn't really matter where you calibrate it, but you can only calibrate it at one point. Where a digital display can be calibrated at every single point on that scale. So what I'm going to do now is going to disconnect this. I'm going to stand up here, get this unhooked from the communications test set. And what we're going to do is now take this cable and hook it up to an antenna. Okay. And what I'll do is, again, same scenario. The center cable, instead of being attached to the communications test set, is now attached to an antenna. That signal comes in here, goes to the power splitter. That signal goes through the 3 dB splitter, and then that signal is evenly split and comes out to both of these radios. So what I want to do is, I'll have to pause the camera unless somebody starts talking here in the next few seconds. Once I get a transmission coming in, we're just going to turn the volume up and listen to them on both of these radios. And you'll be able to see that there's really no difference. They both receive pretty much the same. But what you're going to see is the needle on this radio is going to be a lot, or the display on this one's going to be showing a much higher S unit. And the needle down here may not even move depending on the signal coming in. So even though they're both receiving the same signal, they both sound the same. If it's a weak signal, this meter may not even move, where this one could be on S5. Now, if it was an S9 signal coming into the antenna, or actually it would have to be a little bit more because there is that 3 dB, it's a 3 dB loss type. So you'd have to have an S9 plus 3 dB. But if you had that signal level going into both radios, they would both display S9. But as the signal decreases, this one becomes more inaccurate. So like I said, I wanted to do that because I think that's a common misconception, or it's not so much a misconception, but people don't understand how inaccurate some of these meters can be. Some are better than others. Like I say, digital ones, if they're done properly, and I have seen modern radios that had horribly inaccurate displays as well. Just my noise picking up a little bit there. I saw a couple bars. Now, but there's a good example. There's 3-2. It's flickering between 2 and 3 bars of noise. This needle's not even moving. It's still fully at the bottom of the scale, where this one's flicking between S2 and S3. This one's not displaying anything yet. So, prime example. But so, like I say, we'll wait till I get somebody talking here. It's the middle of the night, so yeah, whenever probably the local mill over here, when a trucker calls in to see what chute to go under, once I can catch somebody talking, I'll fire the camera back up, and we can see that they'll both sound the same. The tone may be a little different because this one, the speaker in this one has a little bit higher pitch than the speaker in this radio, and that also has to do with the receiver circuitry. But you'll hear it's about the same signal level coming in, but one meter is going to be showing a lot higher signal than the other one will be for the exact same signal coming in. And you can see this one was hanging right around S5 when he wasn't talking, so only the carrier was being transmitted. But it was sitting on S5, and this one over here was sitting on S7. Like I say, the closer you get to S9, the more accurate this meter is. The farther away you get from S9, the less accurate it is. We'll wait and see if we can get another conversation on camera here. Okay, somebody gonna start talking? S5.
Sorry, I'll be under 2 minutes.
You see
I'm
that?
sorry, 1 minute.
You can see that weaker station's barely an S1, and this one's like S4 to S5. And that's what I mean by the lower the incoming signal, this one's going to be more inaccurate than, let's say, this radio up here. But if they were both an S9 signal level coming in, they would both display S9. So I hope that kind of clarifies a little bit for people S meters and how they can be inaccurate, and the older ones are less accurate. And like I say, it's not just this radio. It's not an inherent thing in this specific make and model of radio. There could be a problem with this meter. It could be that clock spring could have, the tension might not be right on it over this scale. So it's just less accurate at the bottom end than it is at the top end. And you know, by the same token, you could pull a meter out of a parts chassis, stick it in here. It could be fantastic, or it could get even worse. So yeah, it's one of the problems with dealing with vintage radios is when you can't buy a new meter to stick in. A lot of times you're stuck with what you have for the meter. It does work. And the other thing is, like I say, just because you have a really expensive radio, I could put an amateur radio here on the bench. You know, a radio that costs 10 times as much as this radio, and it's not going to be perfectly accurate. I've seen some amateur radios that are embarrassingly inaccurate over their scale. They may be perfectly fine when you calibrate them for S9, but again, once you start to get off S9, they become less and less accurate. Now, usually they are a lot more accurate, just for the simple fact they're using much better meters in radios like that. But like I say, just because you have a really expensive radio doesn't mean that it's perfectly accurate everywhere on that scale. You stand a better chance with modern radios of having an extremely accurate display, but only if the engineers that designed it and wrote the program, the code that operates that meter, took the time to take very precise measurements for the signal level for every one of the bars on the scale. If they just kind of winged it, those can be just as inaccurate as an analog meter can. So, you know, it's not that one's better than the other. You just stand a better chance of linear accuracy with analog or digital displays like this. So I hope that kind of demonstrates the problem with analog meters. And actually,
Under 2.
Too late. They already gave the shoot number.
Under 2.
And they're back.
Under 2.
So, any case, there you go. There's a demonstration of S-meter inaccuracy and why your meter may not be showing something, but there's nothing wrong with your radio. It's receiving fine, other than there may be a problem with the accuracy of your meter.